Let's move on to the p orbitals. So p orbitals are generally dumbbell shaped with a positive and a negative phase lobe. Which one is positive, which one is negative? It actually really doesn't matter. The key is just that they're opposite. So we have 2px, 2py, and 2pz. And if you look at the probability, obviously because of that node, we call it a nodal plane. It's a plane where the probability is equal to 0. It's 0 probability at the center, but then it has a peak in probability going out. So the two p electrons are on average further out. And note that they do not have a radial, they have one node, but it's a radial, there's no radial node, there's only an angular node, a node in the x, y, or z direction. But if you look at the probability, there's no node going out in one direction. If you start at the origin and go out, say in this direction, you won't encounter any nodes. The only node is the plane there. So that's what they look like. That's a nodal plane. 3p and higher p orbital shapes, I'm going to show you a cool demo in a few minutes that goes into this a lot more. Shapes of d orbitals. So d orbitals have a couple different shapes, but a key is that they generally have two angular planes. So you can see for the dxy that you've got these angular nodal planes, along this plane here and this plane here. You've got a nodal plane. Those two are nodal planes. Same with y, z, xz. Same with dx squared minus y squared. And dz squared sort of doesn't look like it has a nodal plane. It has essentially a nodal cone. I mean, it does look like it's a nodal plane. What it is you essentially wrapped your nodal planes into this two nodal cones there. You notice that there's only one s orbital, there's 3 p orbitals, and there's 5 d orbitals. These orbitals, these are exactly the m equals -2, m equals -1, m equals 0, m equals 1, and m equals 2 orbitals. And I've been a little deceptive here because you can't actually assign numbers directly to all of these. These are all equal. They just, so it doesn't really matter which one is -1. The point is that there's always 5. There's 5 orbitals and there's 5 magnetic quantum numbers here. So with p orbitals, the same. There's 3 p orbitals. Those are the ones that correspond to -1, 0, and 1. Is x -1? No, that's not really relevant. What is important is that there's 3 there and there's 5 for d. And this is what the 5 look like. I would not expect you to be able to draw the 5d orbitals, but I'd expect you to recognize them when you see them. And also, x, y, y, z, don't worry about what the different ones are named, but be able to, if you see an orbital, you should be able to recognize whether it's S, P, D, or F. F orbitals are the one other type of orbital that occur in chemistry, but it's really only important for the actinides and the lactonides. The compounds that are down at the bottom of the periodic table, sort of cut out of the middle. Those are the orbitals that are occupied in that case. So the F orbitals, they get even wilder in shape, and there's, as you can guess, 7 of them. Again, the exact labels of which one is 0, 1, -2 don't matter. Those are essentially arbitrary, but the key point is for L equals 3, there are 7 of them.